Continuing our talk about nuclear chemistry, we're going to look at something called a half-life. And a half-life, or T sub 1/2, as it's mathematically represented, is the time it takes for half of the sample to decay. So if I start out with 16 grams and the half-life is 14 days, 2 weeks, after 2 weeks I'll have 8 grams of the original P32. So I got 16 grams of P32. It's decaying. It's after 14 days, since that's its half-life, I'll only have half of that, which is 8 grams. And then after another 14 days, I'll only have 4 grams. And after another 14 days, or another half-life, I'll have 2 grams. So this is 1 half-life to 8, 2 half-life to 4, and then the third half-life is going to leave me with 2 grams. And so as it's going down, whatever it's producing is going up. The half-life of the isotope is a property of the isotope. It's independent of how much you have, of temperature, and of pressure. So it's just how it is degrading, and so it's inherent in whatever that isotope is. So some common things that we may have heard of that have half-lives. Carbon-14. Carbon-14 has a really long half-life, 5,700 years or so, and so we can use that to date some artifacts in archaeology. Cobalt-60 has 5.3 years of half-life, and we do use that cobalt-60 in some cancer. It's not the greatest thing to use because its half-life is so long, it stays around, and so it can, remain in tissue and things like that for a long time. But it's effective against certain types of cancers. Iodine-131 is something we use a lot for thyroid therapy. We have a lot of iodine molecules that are associated with our thyroid hormones, and so they collect in your thyroid, and so we can use iodine-131 to go in there and destroy some of the thyroid tissue if we need to. Notice it's only an 8-day half-life, and so that's a good thing because, eventually you're going to urinate, and that's going to come out in your urine. Potassium-40 has a long life, and you can use that for geological dating. Phosphorus, leukemia treatment, again, you want a short half-life typically if you're using that on people. Technetium, 6 hours. Okay, technetium is 6 hours. That's the one that's only giving off that gamma ray, if you recall. And then uranium-235, which is one that we use in nuclear reactors, and that is 7 to the times 10 to the 8 years, and so that's why nuclear reactors and the waste produced by those nuclear reactors is an issue, because it takes so long for that to become non-hazardous. So how we use half-life is we can say, okay, if I'm going to administer iodine-131 to destroy some hyperactive thyroid tissue, and its half-life is 8 days, all right, I'm going to give 100 milligram sample exposure to a patient, and I'll need to know how much, if they once they go like a month, like 32 days, how much is going to be left in their body. Okay, because it just halves every time, so it takes a long time for you to get that out, even if it's just days. So you have 32 days, okay, and there are 8 days in one half-life, okay, and the reason they wrote that is because they don't want you to divide or multiply by half, so it's just half-life. Okay, so 32 days, one half-life is 8 days, so it's going to take 4 half-lives to get rid of that material. So it's going to take 4 half-lives. So what you can do, and this is an easy way to do this, is to take 100 milligrams, okay, and say times a half is the first half-life, times a half is the second, times a half is the third, and times a half is the fourth half-life. And so that gives you 6.25 milligrams after 32 days. Okay, so you started with 100 milligrams after 4 half-lives. So you've got 100 divided by 2 is 50. That's 1. Divided by 2 is 25. Divided by 2 is 12.5. So that's 1, 2, 3. Divided by 2 is 6.25. So that's after 4 half-lives.